Nice. Okay, so today I want to start by just talking about some things that I've kind of either skipped a little bit or maybe not addressed. So the first thing is I want to talk about completing the square. Okay, so what I need you guys to be able to do is anytime you are given something in like ax squared plus by squared plus cx plus dy plus e form, you need to be able to have an educated guess about what you think the graph looks like. So, for example, and then if you have an educated guess and you're like, okay, well, I'm thinking it's this, you need to be able to turn it into a conic of that form. And you should have a pretty good idea just by looking at it. So I'm going to run through some examples. So, for instance, what if you had this? Right now, with some degree of certainty, can you look at this and tell me, and then tell me why? Tell me what kind of a graph do you think this is? Tell me how do you know that? And tell me, is there a possible chance that it's not what you think it is, even though you've narrowed it down? There are 4 conics. So of the 4 conics, tell me, and by the way, if you ever don't know this, literally in your notes, it says, how do I determine if it's a conic when it's in this form? And it literally gives you those options in your notes, not the ones you took, but like in the little notes for parabolas, circles, ellipses, and hyperbolas. It'll say that down there. How can you tell just by eyeballing? Why do you think circle? So the coefficients of the square terms are the same. And Lily means not just the actual numbers, but the signs are also the same. So they're both positive, both the same value. And what that will mean is, like right now, if I were to divide through by 3, you can see I get x squared, y squared. And if I start completing the square, I'm not going to have numbers out in front of those x squareds and y squareds. That means that this is most likely a circle. Is there a chance that it's not a circle? Now, I know it's not an ellipse, a hyperbola, or a parabola, but is there a chance that it's not a circle? Well, how could that, if it's not a circle, how could that possibly happen?
It could be a semicircle.
Well, actually, the only way it could be a semicircle is if I had written it with like a square root of something. What could possibly happen on your journey of completing the square? Like, what would be the first step? Do what? Okay, so if when I add the constant to the other side and complete the square, and that I have the 2 factors all set up, but it's equal to a negative, is that even possible? Like hypothetically, this one, when you add 10, you're going to see that that's a positive number, and when I complete the square, I get more positive numbers over there. But what if this had been something like plus 100 right here? Or how about even better? What if it was something like plus 180? Okay, so hypothetically, the first step you make is divide by 3. Right? And then you complete the square with the x's and the y's. So you put the x squareds together. You put the y squareds together. You're going to move the constant over. And look what happens when you complete the square here. You half it square, it's 1. Add a 1 to the other side. Half that square, it's 4. Add a 4 to the other side. And you can see right now, with my perfect square being completed, I ended up with a negative number over here. Is it possible for a perfect square, which has to be positive, no matter what I plug in there, I'm squaring it, right? So when I take that positive number and that positive number and add them together, can I get a negative? Now, I won't know that. I won't know this until I'm finished, right? You can't just look at that number because you're going to be adding stuff to it. But when I'm finished, if that ends up being negative, then this did not end up being a circle. What did it end up being? What would the graph of this look like? Kind of a trick question.
There's no graph. Right?
There's no graph.
Because that's a radius.
So yeah, so you can't have the square root of that would be the radius. You can't have an imaginary radius, right? So literally, this does not show up on the graph. Okay? So first glance, oh yeah, it looks like a circle. But let me make sure by completing the square. Are y'all seeing this? Now, hypothetically, what would happen if this was not 180 up here? What would happen if this was a positive 15 up here? So when I divide by 3, I get a 5, right? And then I subtract that 5 from both sides. And then I go and complete the square. Now what happens? Yeah, what this right here definitely has a value that makes it 0. If I plug in the point -1, 2, which is the center, right? I get a point, and 0 does equal 0. I just don't have a radius with it, do I? What do we call that? I've mentioned it probably once. A degenerate circle. And a degenerate circle is actually a point. Are y'all with me on that? So don't get cocky and look up here and go, circle. Because it could be, and it probably is, of all the problems I've seen in textbooks, most of them end up being that, but it is possible. And you know, you go to a math tournament, and it's not what typically happens. They're always trying to screw you over in any way they possibly can. So they're trying to suck you in and get you to go, circle. So the sucker's going to say circle, but the person who gets it right is usually the person that knows a little bit of everything and can actually go, wait a minute, let me double check and see what that value is in the end. If it's positive, great, you've got a radius. If it's negative, it doesn't exist. But if it's 0, it's a degenerate circle, which is a what? Point. Just a point.
What if you end up with 1 instead of 0? Can it be an ellipse? As if it had 1 on the bottom?
No, the only way ellipse happens, which I'll do that next, is when these numbers are different. Because remember, like, if I end up with a number over here, like 1 or 5 or 10, think about it. If, say I were to end up with, say that number was 12, okay? So when you divide it by 3, it's 4, and you subtract 4 from the other side, and you get this -4 plus 1 plus 4, and you get 1. I mean, that's still a circle. I mean, even if I divide it by something, right, it's still a circle because those values are the same. And you remember, if it's an ellipse, one of them's A and one of them's B, and the A has to be what? Greater than B, right, for it to be an ellipse. See, if you try to graph this like an ellipse, how much are you moving left and right? 1, how much are you moving up and down? That doesn't sound like an ellipse, right? Remember, a circle is kind of like in the family of ellipses. It's just a special one where those are the same. Okay, but you'll never look up this. You'll never look at this at the top and think it's an ellipse if those two numbers are the same. I hope not. Okay, now what happens if? So that's completing the square on this. What happens if the numbers are different? So what if you look up here and instead of being a 3 right there, you see a 6? We'll just make that a, I don't know, something else. Now what do you got? Now I think I have an ellipse. But isn't there a chance, again, that after I complete the square and get everything cleaned up over here and move junk over here, that this ends up being negative? Can I have a squared thing plus a squared thing and get a negative? So again, that would be a DNE. And what if a squared thing plus a squared thing gave me 0?
No, because that's equal to 1.
It would have to be equal to some number, right? So what happens if it's equal to 0? Like, I'll show you that in a second. But if it ends up being 0, it's also a point because, again, and it's a degenerate ellipse, which is a point. Again, a circle is just in the ellipse family, guys. The similarities are alike. So like right here, I'm going to make that a negative. I'll tell you what, I'm going to hold off and decide what that number is going to be. So if you look up here and you see different numbers but same sign, I'm not going to divide through because then I'm going to get a ton of fractions. In this case, I'm going to factor it out. So I'm going to take the 3x squared and the 6x. I'm going to take the 6y squared and the negative 12y, and I'm going to factor out a 3, and I'm going to factor out a 6. Okay? And that's going to give me, tell you what, I want this to be pretty. Let's go with the original problem being -9. So I'm going to move the 9 over and make it positive 9, but I never divided anything, right? Because I factored the 3 out and factored the 6 out. So here's where I am at this present moment, okay? So what would you do to complete the square now? Half of it squared is 1, but what did you really add? 3. Half of 2 is 1, but what did you really add? 6. And when I factor this up, it doesn't quite yet look like a perfect square, but it's equal to a positive number. So that makes me very confident that it's an ellipse, but I still want to be able to maybe sketch it and graph it and tell what it looks like, and I can't do that until this number is a 1. So what do I do lastly? Divide by 18. So I take that number and I make it become a 1. Now in a perfect world, this number you end up with always cancels these numbers nicely. It's just nice that it does that. So when you do that, what do you end up with here? You end up with what? When you cancel that 3, 6. So how did you get 6? You said 18 divided by 3? Sure enough. And then what about this? So you said 18 divided by 6? And of course, 18 divided by 18 is 1. Now, hypothetically, what would have happened if you had this? Because this happens, and for some reason, people just freak out when it happens. What if I ended up with 15 over there? And you're like, well, but wait a minute. 15 does not cancel the 3 and the 6 very nicely. And I have to have it cancel completely. I got to have a 1 there. That's my form, right? So what do? Do you divide by 18 instead? No, because what do you have to have? A 1 over there. So you just suck it up. Now I would probably double check my math, make sure you didn't like maybe forget to go 6 times 1 or something like that. But when you do that, sometimes the numbers cancel nicely, right? And when they do, awesome. When they don't, what do you write? You don't just cancel what does cancel. I mean, you can. Like if I divide a 3 out, but I still have that 2. So what do I write? I can't leave the 2 there. I can write 2.5. Remember, the math is 18 divided by 6 is 3. Well, 5 divided by 2 is 5/2. So just write it as 5/2. And don't worry about it. Your goal is to write it in this form. Are you with me? So if it doesn't cancel nicely, remember what you're doing. 15 divided by 3 is 5. 15 divided by 6, 5/2. So if it doesn't clean up nicely, don't worry about that it doesn't clean up nicely. At least I know there's my a squared term, there's my b squared term. And that was my goal, was to actually find it. You good so far? Okay, so what about this? So what happens when, I'm going to hold off on that number again. What happens if you have this? And I'll fill in that number to make it be pretty or whatever. How can you look at this and tell what it is? It's not a circle because the numbers aren't the same and the signs aren't the same. Hyperbola. It's a hyperbola because one's positive, one's negative on the square terms, right? Now, on the hyperbola, can those be the same? Yes. A hyperbola, the only condition that has to be met is that it's different signs. On an ellipse, the only condition that has to be met is that those are different numbers, right? But the same sign. And remember, ellipses are just a separate, circles are just an extra special part of an ellipse where it's the same sign but different numbers. There's not like an extra special one that's a hyperbola that has the same numbers but different signs. So different signs, you know it's a hyperbola. And by the way, on a hyperbola, you are not going to have a situation that doesn't exist. Because on a hyperbola, you can be equal to a negative. Because remember, we're not adding 2 squares, we're subtracting 2 squares. Isn't it possible to have a perfect square that's smaller and another perfect square that's bigger, and when you subtract them, you get a negative? Right? Or maybe a bigger minus a smaller is a positive. That's possible. It's not possible to add two squares and get a negative. That's why circles and ellipses can be D and E. Hyperbolas cannot be D and E, but they can be degenerate. So if they're equal to 0 at the end, that is a degenerate. But in a situation like this, check it out. I'm gonna hold off on that number just to make this thing pretty. I'm still gonna take the x's and put them together. Take the y's, put them together. Move the constant over. Factor out the 3. Factor out a -2, which changes that sign. And then when I complete the square, plus 1, which is really 3, plus 9, which is really a -18. And let's just say, say this was a -21 in the original problem. So you have, if you put -21 up there, that means you would have added a 21 over. So when all is said and done here, check it out, you get, what, 6? And like any good ellipse or hyperbola, we want that to be equal to 1. So we go and we divide through by a 6. And again, I was waiting on that -21 just because I wanted it to work out kind of nicely. So you end up with x plus 1 over 2 minus y plus 3 squared over 3. Sorry, x plus 1 squared equals 1. And we know that it's a hyperbola. However, what would have happened over here? If instead of having a -21 up at the top, what would have happened if that had been -15? Then you would have added a positive 15. And what would have happened here? 0. And if I get a 0 there on the right, I can't go and divide through by a 0. That gives me undefined. What does this mean? What has it meant so far when we've gotten zeros? Degenerate. It's a degenerate. Now remember, degenerate circles, ellipses, those are points. A degenerate hyperbola is actually the asymptotes. This is an equation, believe it or not, of the asymptotes. I can prove it to you in a second, but literally, if you remember, and I don't know if I've told you this yet, did I tell you that the conic sections were basically slices out of this cone? And did I tell you a degenerate conic is when the slice goes through the tip? Well, the slice on a hyperbola, and this is actually made slightly incorrectly. The slice, and by the way, you're supposed to have a double napped cone, and a double napped cone is a cone on top of a cone. So a real slice on a hyperbola is one that goes directly down. And because it goes directly down, or think directly up, it cuts through part of it, giving you that face like this. But then it comes out and it's in space for a while because the cone got skinny. And then as the other cone gets bigger again, then it cuts into the other one. So you have this slice here that kind of looks like a parabola, but it's really the hyperbola bottom part. And then you also have a hyperbola top part. But what do the edges look like they're following? The asymptotes are actually the edges of the cone. So this slice, as you go through there, actually makes up the edge of the cone. Let me give you a decent picture. Like, what if I gave you this three-dimensional drawing of a double napped cone? Okay? And I start slicing through the top right here. Okay? Now, a slice through the top is going to look something like this. Are you with me? So I'm cutting down through the top, and then right here, it just ends up being in space, doesn't it? And then it enters back in down here and cuts through the bottom part. So you get a top part and a bottom part. Now that's kind of an angled view. Are you kind of seeing it though? You see there's the hyperbola? Now, if I give you this view right here, which is directly in the front, you really see that these are asymptotes. If I cut through right here, you get this section, and then you're out here in space again, and then you enter back in, and you get that section. Are you seeing this? Well, what do these edges make up? The edges of the cone are the what? Are the asymptotes. And this is like the edge of your box right here. So if I ask you what is a degenerate conic, and a degenerate conic slices through the tip, what do you think happens to this cone if I cut straight down through the middle so that it goes through the tip? What do you end up getting out of this cone? Like if I cones on the side of the roads, if I cut it right down the middle, is everybody with me? You just see a cross section. It looks like a triangle. That's the asymptotes. So when you split a cone right dead through the middle, it's in a degenerate slice, all you see is the actual triangle, and the bottom and the top triangle put together give you asymptotes. Now I'll prove it to you another way too. If that was a 0, and there wouldn't be any dividing by 0, right? What would you do to solve for y? Because most lines, which is what an asymptote is, it's y equals. What would you do to solve for y here? Tell me. If I said solve for y, do the math. Right. No, somebody take a shot. What do you do when you solve for y? Well, that's a y-intercept. No, what do you do if I said solve for y? What do you normally do when I say solve for a variable? You do what? You isolate that variable. So move everything else over. So the first step would be to move this over. Okay, so you would do this. And you would subtract all of that junk. Now, if you're saying, well, why don't you multiply it out? Well, you could, but you're going to create a mess. You're going to end up getting this. And I don't want to go back to that. So you subtract it. Then what could you do from this? Again, I'm solving for y. Divide both sides by a negative or a -2. That gets you to here. Right? You with me? Square root both sides. If I square root both sides, my square root goes away. So I get y plus 3 equals plus or minus root 3 over 2. I'm going to have to rationalize that in a second. Times a regular old x plus 1. Sure looks like slope to me. I mean, it's an ugly little slope, but isn't that y minus y equals slope x minus x? And what do you think the plus or minus means? Positive slope, negative slope. What do you see? The asymptotes. Those are the asymptotes of this graph. Are y'all seeing that? So literally, a degenerate hyperbola, if you have it in the right form, is just plugging a 0 in where, like, so if I said, hey, what would the asymptotes look like of this? If I were to give you, and I don't want you to do this necessarily because there's a better way, but if I were to say, hey guys, see this hyperbola? What are the asymptotes? You could just go, those. Because a degenerate hyperbola is the asymptotes. So if I change that to a 0, I would have the asymptotes. But there's a better way. Let me show you. The hard way, because I'm going to ask you to put it in slope-intercept form. So let me show you a little nice trick. Rather than do this, and this would be what you would have to do if you tried it this way. You'd have to subtract that over. Maybe multiply both sides by a -9 to get rid of that. That would change that to a +9. Square root both sides. That would give me y plus 1 equals plus or minus. What does root 9 and root 16 give me? 3/4, and the square root of the square makes that go away. Boom, there are my equations and my asymptotes. But I think there's a better way. And here it is. Both asymptotes always go through what point? Center. And what's the center of this? 1, -1. So couldn't you real quickly, if I said, give me the equation of a line or the equations of the asymptotes, you know the asymptotes both go through the center. Couldn't you go y, change the sign of that equals slope x minus that? And that would jump right to here, right? Now tell me, what is slope defined as? The rise over the run? How much would I be going up and down on this to make my box?
A over B.
Well, it's not always A over B. That's where you got to be careful. Now, sometimes it is. On this one, it's actually B over A. but it is always the rise over run. So what was I rising to make my box? 3. And what was I running? 4. And aren't I doing it both ways? And then you don't have to do any of the algebra.
Like, because the key had something that said A over B, and it just threw me off, and I was like,
and it could be. It could be A over B. But it would only be A over B when your Y term comes first. See, this is my A right here, 4. My B right there, 3. In this case, it's rise over run, so it's B over A. But if the A or the B is in a different place, if the X and Y's are in a different place, then it becomes A over B, it switches. So I don't even remember that. I just think, hey, if I'm going to go sketch my box, and isn't my box what determines my rise and my run, right? Because I always went out the corner of that. So just do rise 3, run 4, plus or minus. And then really, you can find the center and bring it down, or you can just take those two things and bring them down. You don't even really have to think. Just take that, do the rise over run, don't forget the plus or minus. Those are equations of your asymptotes. And equations of your asymptotes are the degenerate hyperbola, should you have a degenerate hyperbola. So if you ever see this equal to 0, or as you're completing the square, you get this equal to 0, if you see that, that means that it is a degenerate hyperbola. Are y'all with me? Now let me throw you one last little curveball. What happens, it's not a huge one, but what would happen if how about, what if that negative 15 were positive 6 in the original problem? So that your first step, you subtract 6 from both sides. Actually, I didn't want that. How about negative 3? How about positive 3? So let's just say there was a positive 3 there. You subtract 3 from both sides. And then when you complete the square, what do you end up with? Now again, had this been a circle and an ellipse, or an ellipse, there's no way you can add 2 squares and get a negative. We would say D and E. But here, it's a hyperbola. You can subtract 2 squares and get negative as long as the second square is bigger. So this is possible. So what would you do? How do you get this in the final hyperbolic form? Divide by negative 18? Now, I wouldn't do that if these were both positive. I'd say D and E. But look, if I divide by negative 18, I just end up with x plus 1 squared over a negative 6 plus y plus 3 squared over a 9 equals 1. And what would I do to put this in the right form at this point? Because it doesn't look great here with the negative and then the positive. Switch those. So every now and then you get down to here and you go, oh, that's the positive term now. So y plus 3 squared over 9 minus x plus 1 squared over 6. You tracking with me? Yes, no? So if you had now that you have this, you should be able to answer all the questions you possibly could want about that. But remember, if I ask you right here and say, hey, right here, give me the equations of the asymptotes. Don't work too hard for that. Don't feel like you got to change that to 0 and then do a bunch of junk. Because all you have to do is go take the center, which is the y plus 3, and the x plus 1. Remember, these are lines, so don't go and square that and turn it into a parabola, right? And I need the slope. What am I rising on this? When you mark the box, what did you rise up from the center? You rose up that, so 3. What did you run left and right on the box? Root 6. And then don't forget plus or minus. And of course, we want to rationalize. So you get y plus 3 equals, and when you do a root 6 over a root 6, you end up getting plus or minus root 6 over 2. So it's kind of an ugly looking slope, but are you good? Okay. So asymptotes and conic form, and then in the rare case that this happens, there's just no x squared term at all. What do you do there? Then it's a parabola. Okay, and if there's only one squared term, it's a parabola. I can't give you something that's a parabola and then it end up being anything other than a parabola. I can't like give you one and you go, oh, I think it's a parabola, but it might be DNE. No, it will always be a parabola. Oh, but wait, it might be degenerate. No, it will always be a parabola. There are degenerate conics. Like there is such a thing as a degenerate parabola. It's a line. Because a parabola is created by slicing this cone parallel to the side. Parallel to the side gives me this. A degenerate parabola is made by slicing parallel to the side but through the tip. How do you go parallel to the side and also touch the tip? What would you have to do? You would just be skimming that edge, wouldn't you? So if I skim that edge, I'd have to actually have a line. But what do lines don't have x squared terms in them, do they? So there's no way I could write a degenerate parabola actually looks like a line. And I don't know anybody that's going to look at this and go, oh, I see what you're doing, Mr. Hurry. Sneaky, degenerate parabola. I mean, it's just a line, right? So it's not like I can sneak those on you like I can with the other degenerates or the other DNEs. Is that making sense, all of this? Okay. I know it's a lot to throw at you, but remember, your test is not tomorrow. Your test is not till Thursday. So you still have some days to practice. I would encourage you to get some of that practice in tonight and start feeling good about this, because you could always drop by and see me tomorrow after school and ask questions. And then remember, we're going to do the review game. You're going to learn a little bit maybe, because I'll throw some curveballs at you in the review game, the conics game, whatever. And then you can always come by Wednesday, but I wouldn't wait till Wednesday night. It's a lot of material we're covering. All right? So if I was given this, what kind of parabola is it? Could you tell me right now just by eyeballing? I mean, when I say what kind of parabola, is it a one that either goes up or down or one that goes left or right? Now remember, what did we learn? On the section before, we learned that these did what? But these went up or down, correct? Because I had an x squared term. What do you have now? A y squared. So if it's a y squared, you're starting with x. Which way is this one going? It's got to be going left or right. But ultimately, you don't have to decide that right this second. What you do need to do, though, is get your squared stuff on the right, because that's where we want the squared stuff. So I am going to I'm going to take anything that's squared and variables that go with it and move it over to the right. So I'm going to leave the 6x plus 3. And I'm going to add that over, and I'm going to add that over, and then I'm going to begin the process of completing a square. So what would you do first if you're completing the square? Now, if you divide by 2, which is fine, you end up getting a fraction down there, and I don't want fractions on the right side. So I would take it out, and the nice thing about taking it out is I do want to have an a term. So what I'm going to do is factor that 2 out, because it even looks like it might be an a term, even though it's going to change in the end. Factor it out. That's why you need to begin with the end in mind. Know where you're kind of headed. I'm not headed to that. I'm headed to, x minus h and y minus k. But I know that because of this square term, I know that that's about to happen. So beginning with the end in mind tells me, oh yeah, I want to factor that out because I want to see it there in the end. And then completing the square gives you what? What did I really add though? 18. So I get 6x plus 21. I complete the square, and am I finished? What would be my last step if I want to make it look like this? It looks like this except for one number. What is it? 6 can't be there. It's got to be a 1x, not a 6x. So what do? Divide everything by a 6. And then right here, you got to divide each one. That's the distributive property with a plus. That gives you x plus 21/6, which is 7/2. And then here, what happens? I'm just going to cancel that and leave it as a 1 over 3. So 1/3 y plus 3 squared. So make sure you can do all the completing the square. Make sure you understand all the degenerate stuff. What does the degenerate look like? Can there be degenerates? And I think you'll be in good shape. Yeah.
Are you gonna ask anything about, like, ask us to define the degenerate parabola?
I won't ask you to define it, but I might give you one and say, what kind of conic is this? Like, for instance, I might give you that and say what kind of conic it is. Or I would say something like maybe, okay, if you had this, what would the graph of this look like? And you would say, oh, well, it's going to look like a pair of intersecting lines, because that's what asymptotes are. Or maybe I go, what's the graph of that going to look like? And you're going to say, it's not an ellipse if it's a zero. You're going to say a point, because that's a degenerate ellipse, right? Or I might say, all right, what does this look like? Well, that's just a circle, right? I mean, if I have something squared plus something squared equals a number, that's a circle with a radius of root 20, right? And then I might say, what is this? A degenerate circle, which looks like a what on the graph? A point. Or I might say, what is this? That does not exist, right? Or I might say, what is this? That does not exist. That's like an ellipse. Ellipses and circles. You can't add two positive things and get a negative. I might say, what is this? That can still be a hyperbola, right? Because you can have something squared minus something squared and get a negative. The only thing that happens here is when you divide through by that -6, you end up getting the negative out front, right? Are y'all tracking with me? So you would end up getting that, and then you would have to switch the order of these to make sure that the negative came second, the positive came first. So those are the kinds of questions I might have. But no, I'm not going to go, hey, give me the best definition you have for a degenerate hyperbola. And then you would have to come up with, well, it's a slice of the cone that is perpendicular or parallel to the axis going through the cones, but also running through the tip of the double napkin. No, I'm not going to. Right? Okay. And I guess, does anybody have a question for me?
Yes, can you work 33 from home?
Do you remember what it was given? What was given?
I have it. I think I simplified it more if I wrote it down. But
That's okay. Do you remember what page it is?
422.
422, number 33. The square root one? Okay, so it says graph each equation. Each graph is a semi-ellipse since root A is always non-negative. Blah, 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 whatever. You could always come in here and plot a bunch of points if you really wanted to, and you could probably get a decent looking graph. But let me just show you the mentality of this. The mentality is, have no idea. Now, if you'd had a normal Helmer spring, you would have learned that that right there is a semi-ellipse. Anything written as a number minus x squared under a radical is a semi-ellipse. You would have learned that. I'm sorry, is a semicircle. That you would have learned. And then by putting a number out in front, all I do is shrink the semicircle. So you go from a normal semicircle to a less tall semicircle. But you would have learned that this was the semicircle equation. But you didn't get that because last spring was a disaster. So what we would do is go, well, let me change the way this looks. Let me get rid of the square root. And then maybe it will look like something. So I'm going to square both sides. When I do that, I get 1/4, and the square root goes away. And it still doesn't look that pretty to me. So maybe I distribute the 1/4 in there. And that gives me 1 minus x squared over 4. Now it starts to look better to me now. So now I can go, wait, what if I added that over to the other side? I would have x squared over 4 plus y squared equals 1. Now if you ask me, all I got to do is put a 1 under that y squared and it looks like an ellipse. Right? Now here's the problem. It's not an ellipse. The book told you it was a semi-ellipse. But this at least lets you know how to sketch it. You could say, all right, left and right 2, up and down 1. So my ellipse is going to be in this form. And then I go back to the original problem and go, wait, the original problem said y was always equal to positive 1/2. Y can only have positive values. And if y can only have positive values, could I possibly have points that go below the x-axis? Those would be negative y values. So I get rid of those and just keep that part. Now, if this had been a negative up here, when you square both sides, it still goes away, right? I still get the same result. But this time I go, wait, it's not an ellipse. It is a semi-ellipse. So y would only be negative. And I would go back and keep only the negative parts. Or wait, what if that was an x and that was a y? Now what would this look like? Sorry. I don't know why I have y here. That should be 4. Sorry.
Right.
Oh, sorry. X squared. I changed this. My bad. So in this case, this is actually what? Left and right 1, up and down 2, and you'd be tempted to sketch this whole thing in there, right? But wait. X is always negative. So what do? Keep the left side, get rid of the right side. But again, I guess you could just plot points all day. But it's a whole lot easier to do it this way, I think. So whenever you see semi-ellipsis, parabolas, hyperbolas, anything on your test as a square root, square both sides, and then try to make it look like one of the forms we have. Sketch that form, and then go back to the original and say, if x is negative, keep the left. Y is positive, keep up. Y is negative, keep down. X is positive, keep right. Now, it really boils down to just that. 4 minutes. Anybody have any other questions on anything? Guys, start diving into these review sheets. Really spend some time tonight and expose yourself. And then if you have questions, text me, whatever. Send me an email. Come by after school. But remember, test Thursday. You've got plenty of time to practice and put all this together. But don't wait till the last second. It's just too much material. And I would make some flashcards if you have trouble memorizing stuff. That's such a great way because you can go through your flashcards when you don't know them. Keep those in the pile. When you do know them, take them out of the pile, and you can really whittle it down and get in a good place. All right. Good chat.